So during today's lesson, we'll focus on, first of all, the area of a sector within a circle, okay? In order for us to continue with the discussion of our vocabulary in context, first of all, a sector of a circle is going to be the region which is bounded by two radii of the circle and their intercepted arc, okay? So first of all, here we have our circle with center O, okay? So here we've colored the sector of a circle in red. And notice here it is a region within a circle, and it's going to be bounded by two radii of the given circle. In this case, the radii is represented by segments OS and by segment OF. Okay, so they are the two radii, okay, of the circle, okay, and they are part of the sector of a circle, okay. So these would be the two radii and their intercepted arc, okay. Notice here that the intercepted arc is going to be minor arc represented by FS. So it would be minor arc FS, okay. Notice here that the small sector, which is the red one, is defined as minor arc FS or minor arc SF, okay? And we also have the major arc, which is going to be the large sector, okay? We have a small sector and we also have a large sector, okay? So the large sector is going to be represented by major arc FGS if we're moving in this direction, or SGF, okay? So now we know the definition in context of a sector of a circle. Now let's go ahead and continue. Now, the ratio of the area of a sector of a circle, okay, is to the area of the whole circle, which is pi times r squared, this is the area, as the ratio of the measure of the intercepted arc is to 360. So here we have a proportion, and by definition, a proportion is going to be represented by here, our equality sign. To the left side, we have a what? We have a ratio, and to the right side, we also have a ratio, okay? So we're saying here that the area of a sector, which is this red area, okay, is to the area of the circle, which is represented by pi times the square of the radius, is going to be equal to what the measure of the intercepted arc is to what? Is to 360 degrees, okay? In this case, the intercepted arc is the minor arc is going to be FS. So here we establish a relation between what? Between the minor arc FS and what? 360 degrees. Why 360 degrees? Because that represents the measure of one full rotation in what? In degrees, okay? Now, if we want to find the area of a sector, okay, what do we have to do? We have to eliminate the denominator, which is represented by pi times r squared. So mathematically, what we do in this particular case is we multiply the left side of the equation and the right side of the equation times by what? By pi times r squared. That means that on our left side, pi times r squared, this denominator would be eliminated. And hence, we have the definition or the formula of representing the area of a sector, which is going to be the measure of the intercepted arc. You divide it by 360 degrees. Notice here that we will continue working with the measure of the intercepted arc expressed in degrees, because if we're going to divide by degrees in the denominator, in our numerator, we also have to have a measurement of the circle or a part of a circle also represented in degrees. So the measure of the intercepted arc in degrees divided by 360 times pi times r squared, that's going to represent the area of the what? The area of the sector, which is this red shaded area. Okay, so now let's move on with sample problem number 5 in our presentation. Okay, we need to find the areas of the sectors formed by angle TOB. Okay, leave your answers in terms of pi. Okay, first of all, we are given a circle with center O. Okay, we are also given an angle formed by TOB. Notice that the vertex of this angle is going to be what? Is going to be O. And O also, point O, also represents the center of the circle. Okay? By definition, recall when we began studying the circles, angle TOB is defined as what? It's defined as a central angle. Why? Because its vertex is going to be the center of the circle. And by definition, we also studied that the measure of minor arc, TB, is going to be equal to the measure of what? To the measure of the central angle TOB. Okay? Now here, we have to find the areas of the sectors. Notice that here we have a small sector, which is TOB, and we also have a large sector, which is going to be what? Sector TGB. So the small sector here, it's represented by what? By the center O and by what? Points T and B, which are parts of what? Of the small sector. Okay? So in order for us, and we are also given that radius OB, okay, which is the same as radius OT because they are the radii of the circle, they measure 7 inches. And we are also given that the measure of angle TOB is 123 degrees. Okay? Now, here, the measure of minor arc TB is going to be equal also to 120 degrees. Why? Because of what we just mentioned. And it's the fact that the minor arc, the measure of the minor arc, is going to be equal to the measure of its central angle, which is going to be 120 degrees. Okay? Now, the measure of major arc, TGB, is going to be equal to 360 degrees minus what? Minus the measure of the minor arc, which is 123. So that tells us that the measure of major arc, TGB, is going to be equal to what? To 237 degrees. Okay? Now that we know what the measure of minor arc TB is, and we also know what the measure of major arc TGB is, we know those two measures. Now we're ready to find the area of the small sector and the area of the larger sector. Okay? So we apply our formula, and in order for us to find the area of the small sector, okay, it's going to be the measure of minor arc TB divided by 360 times pi times the square of what? Of the radius, which is given. It's 7. So the area of the small sector is going to be 123 degrees, which is the measure of minor arc TB. That's 123 divided by 360 times pi times 7 inches. If you take 7 inches and you square it, 7, okay, to the second power is 49, and here we take our inches and we simply square them. Okay, so after we perform our operation, the area of the small sector is going to be 16.74 times pi, because remember we have to leave our answer in terms of pi. Okay, so it's going to be 16.72 times pi square inches. Okay, now in order for us to find the area of the larger sector, we do the same thing. But instead of using in our formula the measure of the minor arc, we're going to use the measure of what? The measure of the major arc, which is TGB or BGT. Okay, so that's going to be 237. Remember, this was 360 minus 123. It's 237 divided by 360. Again, we have to leave our answer in terms of pi. So we just simply bring our pi down, times 7 inches squared, the same. It's 49 square inches. Okay, so after we perform our operation, the area of the larger sector is going to be equal to 32.26 times pi square inches. Okay. Now we continue with the definition in context again of the area of a segment. Okay. To find the area of a segment, we simply subtract the area of the triangle from the area of the sector. But before we move on with this definition and the application of the definition, first of all, let's visualize what we have. Again, we have circle O, okay? And then within circle O, we have a sector, okay? And notice here that the sector consists of what? Consists of this red triangle plus this green base. This green base, this green base is called the segment, okay? And then on top, we have the triangle, okay? So that means that the area of the sector, which consists of these two pieces, and those pieces are, first of all, the area of a triangle plus the area of a segment, okay? Now, if we are, excuse me, if we're going to find the area of a segment, okay, by our subtraction property to this equation, we have to subtract the area of the triangle in both sides. So that means that the area of a segment is going to be equal to the area of the sector, the whole sector, minus the area of what? Of the triangle, okay? So let's go ahead and move on with sample problem number 6. Now, we need to find the area of the green segment, which is this segment, okay? We already know that by definition, the area of the green segment, okay, this piece here, is going to be equal to the area of the sector, which consists of what? Of the triangle plus the segment. So it's going to be equal to the area of the sector minus the area of the triangle, okay? So first of all, we have to work on finding the area of the sector. Then we subtract it from the area. We subtract the area of the triangle from what we find representing the area of a sector. Okay? Now, in this problem, we are given that line segment IP, which is equal to line segment IM. Why? Because both segments represent the radii of circle what? Of circle I, okay? So the measure of IP and IN, which are the radii, it's going to be 8 meters, okay? Now the measure of angle NIP, which remember, since I, okay, point I is the center of a circle, angle NIP is going to be the what? The central angle. So that's going to be equal, it's given. It's going to be equal to 150 degrees. Again, we have to find the area, this piece, the area of the segment, which is the green piece. Okay, so step number 1. We need to find the area of the sector. Okay, by definition, we already learned that the area of the sector is going to be equal. This sector, remember, since the central angle is equal to 160 degrees, that means that the measure of minor arc NP, by definition, it's always also going to be equal to 150. So the area of the sector, NIP, represented by NIP, is going to be equal to what? To the measure of minor arc NP, which is 150 divided by 360 times pi times what? The square of the radius. In this case, it's equal to what? 8, because it's given. Okay? after we perform our operation, the area of the sector, which is represented by what? NIP is going to be equal to 83.7 square meters. Okay? Now we need to work on the area of the triangle. Okay? Now, notice here, if we're working with this triangle, NIP, okay? Let's focus right here, okay? So what we really do have, it's going to be an isosceles triangle, okay? Both of the radii is going to be equal to 8. They have the same measure. Why? Because we're looking at the distances represented, the distance from I to P and the distance from I to N. Now, since I is going to be the center of a circle, that means that now we have an isosceles triangle, okay? And notice that both of the radii are going to be equal to 8. And right here, we have our base, okay? Now, by definition, we know that the area of a triangle is going to be equal to 1/2 times the base times the height, okay? So the strategy here would be for us to find the measure of the base of the triangle and the measure of the height, okay? We plug in our values and then we take 1/2 of what we get, okay? So we're going to extract this red isosceles triangle and we're going to position it right here, okay? Notice that the distance from I to P and the distance from I to N, it's the same. They're the radii. They measure 8 and they measure 8. Okay, so what we're going to do, since point I represents the center of the circle, we're going to throw a perpendicular bisector beginning at point I and ending here at point M. Okay, so recall, if we're throwing a perpendicular bisector, okay, from point I to this point M, which lies on line segment NP, that means that M is going to be a midpoint. So M would be the midpoint of what? Of line segment AP. Okay? Notice that after we throw that perpendicular bisector, we get to what? We get 2 right triangles. Okay? And notice here, since angle NIP, which is the central angle, it measures 150 degrees, and line segment IM represents the perpendicular bisector, that means that this angle measures 75 and this one measures 75. So what we need to do, in order for us to find the base, we have to find the distance from N to M, which is going to be equal to the distance from what? From M to P. Now, we also have to find the distance from I to M, which would represent the height, okay, of both triangles, okay? So after we get those 2 results, we add the distance from N to M plus the distance from M to P, and that would be the base. The height would be the distance from I to M, okay? So first of all, in order to find the distance from M to P, okay, we have this right triangle. This angle measures 90 degrees, okay? So we know that this angle measures 75 degrees. So in order for us to find the measure of M to P, which is represented by X, we have to use trigonometry. So we have to think about the fact that if we have the measure of this angle, which is 75 degrees, okay? Now, what trigonometric function establishes a relationship between the opposite side of angle MIP and its hypotenuse, which is IP? Because this is a 90-degree angle, remember, the opposite side of the 90-degree angle would be the hypotenuse, okay? So we're looking for X. We have the pi hypotenuse and we have the measure of the angle. So in this case, we use the sine function. The sine function helps us establish a relationship between the opposite side of angle MIP IP, or angle I, and the hypotenuse. Okay, so we say that the sine of 75 is going to be equal to x over 8. Okay, now when we do our cross multiplication, the sine of 75 is over what? Over 1. So x times what? X times 1, excuse me, x is going to be equal to the sine of 75 times 8. So x is going to be equal to 0.9659, which is the sine of 75, times 8, which is equal to 7.72. So since m, remember m is the midpoint, okay? If the distance of m to p is equal to 7.72, that means that the distance from m to n is also equal to what? To 7.72, okay? So that means that the base of the triangle is going to be equal to 7.72 times 2, which is equal to 15.44. Now we need to find the height, okay? Now, again, we have the measure of angle I, which is 75 degrees. Now, what trigonometric function would help us establish a relationship between the adjacent side of angle I and the hypotenuse of the right triangle? So that would be the cosine function. We apply it, and then we say that the cosine of 75 degrees is going to be equal to its adjacent side, which is represented by y, over the hypotenuse, which is 8. We perform our cross multiplication in order for us to solve this proportion, and what do we have? We say that y is going to be equal to the cosine of 75, which is 0.2588 times 8. Okay, so that means that y is going to be equal to 2.07. Remember that this 2.07 represents what? The height, which here is represented by what? Our variable, which is y. Okay, now, in order for us to find the area of the triangle, it's going to be equal to 1/2 times the base. Remember, it's 7.72 plus 7.72, or 7.72 times 2, which is 15.44, times the height, which is 2.07. That means that the area of triangle NIP is going to be equal to 16 square meters. Now finally, step 3 would be substitution. By definition, the area of the segment is going to be equal to the area of the sector minus the area of the triangle, okay? So substituting the two values we've already obtained, the area of the segment is going to be equal to the area of the sector, which is 83.7 square meters, minus the area of the triangle, which we just calculated, which is 16 square meters. That means that the area of the segment is going to be equal to 67.7 square meters. Okay? So we'll leave it here for today. This would be a great help, this instructional video. Complete these problems, and I'll see you next week. Have a great one. Bye-bye.